Now we're going to practice applying what we learned in the last video. Make sure to pause and try each problem on your own before watching the answer. And this is going to help you get a lot more out of the videos. In this example, we have an unknown that travels faster than a given molecule. And I ask you a bit of a stepping stone / check question first. Given this, is the mass of the unknown heavier or lighter? Pause before you hit play and listen to the answer. Since it's traveling faster, we know that our molecular mass must be lower, and so the gas is lighter. This is good to check beforehand because it checks and makes sure that when you get your answer that it makes sense. From here, we can fill into the ratio that we set up in our earlier videos. Filling in our ratio, as is, with the 1.55, means that our lighter gas or our faster gas is on top. If we fill in the 1.55 as is, as our R1, R2, that means that our unknown mass is going to be our M1, or is going to be on the bottom. This means that our propane molecular mass is 44.08 and is on top. From here, we can do some brief rearrangement and get our molar mass of 18.3 grams per mole. Now in this example, we have several gases, and I ask you to rank them in two ways. First, I ask in order of increasing speed, and then increasing time. We know that heavy things move slowly, so for speed, we will start with our heaviest, or our slowest, and move on to our lightest and fastest. So we'll start with our N2O5, moving to our argon, to our nitrogen monoxide, to our nitrogen. Now, for time, it's actually going to be the exact opposite of this. Something that is very heavy moves slow, and so therefore it takes a lot of time to effuse. Therefore, we will list our lightest and fastest first, given that that takes the least amount of time to effuse. And then we'll slowly move on to our N2O5, which is our heaviest and our slowest. Let's use that example that we just did and now do a mathematical version of the problem. Here we are going to use time as a ratio rather than speed. Now we just discussed how the faster that something effuses, the less time it takes. Or in other words, the rate and the time are inversely proportional. So we flip-flop the ratio for time. From here, we can simply fill in our values as we always have. We put our 12.6 on top, which is now related to our 44 grams per mole. We put our 28 on top, and we solve for our time. Once we get our 15.8, let's make sure that it makes sense. We know that carbon dioxide is heavier than carbon monoxide, and so it should take longer to effuse. And in fact, 15.8 is a longer amount of time than 12.6 seconds, and so we probably did everything correct. This is a really good check when you're doing the ratios to make sure that you didn't fill in the wrong order. Now for our last one. Notice here we're actually going to backtrack a bit and use our original URMS equation to set up a new ratio. We want to know when two gases are the same speed so that we can set these equal to each other. We have our temperature of our UF6 and our H2. In this case, I'm asking when are they the same speed? So we will set these two equations equal to each other. All I changed from one to the next was the labels and the subscripts to keep track of everything. We can cancel out our square root, our 3, and our r without really having to do any work because those are all constants and you do the same thing to each side. We can then fill in our values. From here, we use our periodic table to get our grams per mole. In this case, because our r's canceled and we're not using r, we are actually able to go ahead and use our grams per mole as is. We don't have to convert to kilograms. And then we can convert to Kelvin and fill in. In this case, we now have our temperature of our UF6 must be 5.40 times 10 to the 4th Kelvin in order to be the same speed as hydrogen.